Alright guys, so in this video we will be talking about multi-master replication, which is also known as multi-primary replication algorithm. Alright, so in our last video, if you are following up my replication series, you must know that in our last video series we discussed about single master replication and we did a deep dive into it. So in this video we will do a deep dive into multi-master replication. So let's quickly begin with it. So in single master replication, we understood that in a distributed system, right, where all nodes servers are kind of connected via a network. So those nodes are talking to each other in terms of sharing data and sharing a lot of things. But in the network of multiple nodes, only one node will be designated as a leader, right? And all the write operation will be happening via that leader. However, the read operations can be happen via any of the node replicas, the follower replicas, right? So we had the leader and we had the followers. All right, so let's, in the multi-master replication, we have the same scenario. The only difference is it allows more than one node to accept writes. So let's do a comparison quickly. In single master replication, we only had one node, one leader, and then in this multi-master replication we can have multiple masters that can accept writes. In single replication, that leader, only single leader can accept the writes, and read can happen via the other followers replicas as well. But in this multi-master, write can be happen from any of the leader node. You can have a multiple leader nodes across the distributed systems, right? So that's the basic difference. You can have, so write will be faster because you will have multiple leaders, right, across the distributed system. So now, in order to understand multiple replication quickly, right, or in depth, right, let's first quickly recap our single master replication. So how write used to work in single master replication? So there were two ways, right? Synchronous replication and asynchronous replication as part of the write operation. And if you are not following up my replication series, I would suggest you to go back and in my YouTube channel just search for single master replication. You will end up getting a video. Just go through it, watch till the end. You will get an idea, okay, what is single master replication? What are we actually talking about? But I'll try to spend like 2-3 minutes to make you understand single master replication. So as part of the synchronous replication, right, let's say if client is trying to update the username to XYZ, it will go to the leader node. Now because all write will happen via leader node, and then leader is the responsibility of reader node. Once it write it locally, then it will propagate those changes to the follower replicas, right? And then those follower replicas could be anywhere in the distributed system. So distributed system, let's say you could have 3-4 data centers. Maybe one follower node is data center 3 and one follower data center 4 and 2 followers in data center 1. And the way asynchronous replication works is, if client is writing to reader node will write it locally and then propagate that change later on, right? So the entire system will be eventually consistent. And the first use case, the system will be strongly consistent because the write operation is only getting complete when the write operation gets complete among all the follower replicas, right? But that's not a case with async. You only writing it in first place and then the other follower replicas are getting updated eventually. Alright, so this is strongly consistent situation, and second one is the eventual consistent system. So let's move on and quickly and try to understand then this from the data center perspective. So let's say you have your client. Well, I already told you, right, whenever I say client, that actually means someone, a device kind of, who is actually consuming your data. So, or you see, distributed system, all these things happens behind the scenes, right? Let's say if you are using Kafka. What is your Kafka? Kafka is also using a replication, right? Because if you see, Kafka also replicate your data among the different brokers, right? So Kafka is following a single master replication. And then there are many other tools and software systems that are using multi-master write applications, right? For example, CouchDB. And then there are other versions available for Postgres and MySQL, where you can tune in the multi-master replication in the MySQL and Postgres. So now, if you see here, right, in the single master replication, so you will see that this client is trying to update the username XYZ, right, and that write operation is going to your leader node. All right, now you have three data centers: data center 1, data center 2, data center 3. So you have your leader node in data center 1, let's say. So that write is happening at data center 1, and in the same data center you have another node, right, which is acting as a follower replica. So write will happen at the leader node locally first, and then this change will be propagated to the data center 1 follower and respectively to data center 2 and data center 3 follower nodes, right? So that's how your single master replication works. And in case your leader node goes down for, let's say, some reasons, then one of the follower nodes, there will be a leader election will happen. So this could be anything. This failover can be anyway, right? It could be manual, it could be automatic, but eventually there will be a leader. There will be a leader election algorithm will get implemented, will get executed, and then one of the follower node will become the leader again, and then all those things will get restored and start working. So now that is how your single master works, right? So now let's move on and understand how your multi-master works. So this is your multi-master replication scenario. So let's say you have multi data centers. You see, you have data center 1, you have data center 2, you have data center 3. Now each data center, right, has one leader node. It doesn't mean that, okay, every node will act as a leader node. No. So let's say what is a distributed system? Distributed system is your overall architecture, the way it has been deployed or being executed is it is distributed across the globe, right, but connected via networking, talking to each other and sharing data, right? That's your distributed system. So let's say you have multiple data centers. For example, let's say you pick up any cloud, they have multiple data centers. If you are using on-prem, you can have multiple data centers. So let's say your database system, consider this as a database system, and it's being deployed across multiple data centers, okay, and different regions. Now each data center will have a leader node designated, right? So now let's say when your write happens, so write can happen in any of the data center, right? But the eventual concept is, but the thumb rule is that write will be propagated to other follower nodes. For example, if your client is trying to update username is equal to XYZ, let's assume for some time. Now this write, let's say, happens at leader node at data center 1. Now what will happen is data center 1 leader node will propagate this write update to its follower nodes, right, here and here, and also will propagate this write operation to data center 2 leader node and data center it's a writing mistake, data center 2 and data center 3 leader nodes, right? So this leader node, it will first data center 1 leader, it will update its followers, also propagate the change to the leaders of data center 2 and data center 3 here and here, right? These bigger nodes, although they won't be bigger nodes, these are same size, but I've just to indicate in the diagram I have make it bigger. So this change will propagate it to leader data center 2, leader data center 3. Now these leaders in the data center 2 and data center 3, now it's their responsibility to propagate the change in its followers. So you have 2 followers in data center 2 and 2 followers in data center 3. So now this leader will receive the write operation that, okay, username XYZ has been updated, so it will update it locally first, right? So after updating it locally, it will propagate that change to here and here, and same things will work here as well. So this leader will write this operation, this write operation username XYZ is equal to the leader node locally, and then will propagate the same change to the followers here as well. So now you see this, if you see, right, this, what was the problem in the single master replication? I don't know if you remember it. We already discussed in the end of the lecture, and we discussed that because of the fact that write is happening only at the leader node, so write operation will be slower. However, read operation will be faster because you can read from the follower replicas as well, right? In the multi-master, the major benefit you see in the multi-master architecture is it will have a better performance in terms of write, right? Because you see, you can go and write anywhere, right? If you go back, your client can write to data center 1. In this diagram, it's writing to data center 1. But let's say there could be a client which can write at data center 2. And there could be a client which can write a data center 3 here and data center 2 here, right? So all those write operations can happen in any of the data center. Now from that particular data center, that particular write operation will be propagated. Now by this time, now let's think about it, right? Anyways, after 1 or 2 slides we'll be reaching to that point. Think about it that if write can happen at multiple places, right? Let's say there is I have a profile account and I have a username. I have a YouTube username, let's say Suchit. Now if I am updating this username Suchit, right? Or let's say let's take some other example. For example, there is some a profile or let's say any story, right? Or any document, or if someone can an individual can update the same document at data center 1, right? That let's say the same document gets updated at line number 2, and that write operation goes to data center 1, right? And for the same line, the same document, that data center, there is another write operation, data center 2 received, right? So let's say somebody has written on that particular line in the same document, Google Docs, somebody has written A and somebody has written at data center 2B, right? So those are two different values at same position. So it's a conflict situation. So although it's faster, it has a better performance, but there are certain issues with it as well, right? And you must be able to think about it, because the moment I said okay, multi-master can accept writes at multiple data center places or multiple places, let's make it generalized. So let's go back to benefits. You see, I said benefit is it has a better performance because of the fact it can accept write at multiple places, because you have multiple leaders, each leader can accept your write operation and further propagate it, write it locally, and can further propagate it to your follower replicas. Now it can also save you right from your data center outage. So now think about a situation that in this particular situation, for some reason there is some network or infra issue, right? And then data center goes down, right? Or let's say your leader node in data center 2 goes down, right? Think about the single master replication case. If your leader node goes down, right, what will happen? Leader election will happen, and then that will take some time, that there will be some delay involved, and then after some time system will be restored, all the write operation will get continued. But in this case, if your leader node at data center 2 goes down, what will happen? Nothing will happen, right? System will not get impacted because you still have other leader nodes in data center 1 and data center 2. So write operation will be very smooth, and that is the reason I have written data center outage tolerant. That means it has tolerance to your any outage that happens in your data center or any outage that happens with your leader node. And same thing with your network outage tolerant. So let's say your system's been connected with network, or if anything goes wrong, let's say with the network, right, and your system are not in the situation to talk to each other. In that case, what could happen is, because this whole scenario, the way these guys are talking to each other is asynchronous, right? Because this cannot be a synchronous operation. You see, if somebody is writing a leader node data center 1, it cannot happen like that. Okay, it will first update the leader node 2, first update the leader node 3, it will update all the followers, and then you will say, go back to the client and say your write operation is successful. No, it won't work like that. If you make it work like that, there will be a lot of issues. You will end up having a lot of issues. So the way it works is asynchronous, right? Even if you make a change at data center 2 and here, and there are changes continuously being done at data center 1, and these two data centers got disconnected from the network perspective. Changes can happen data center 2, nothing will happen. Changes can keep on happening in data center 1, but the moment these two data center gets connected again, or let's say data center is very at broader level, or let's say these two leader nodes gets connected again, they can start sharing the data again. And then although there will be some conflicts, right, it will say no, the value of x is equal to 10, and then it will say no, x is equal to 20, right? So we will have to basically use a conflict resolution solution here to reach to a single value, the correct value. But that's a separate topic. But these guys, this whole setup, this multi-master replication setup is a network tolerant, outage tolerant, right? Because if anything happens in the network, if there is an outage with the network, all writes can happen, and then nothing will get impacted, and whenever these guys gets online and connected again, they can start sharing the data. Okay, so by this time I have already spoken about the benefits, and I have already spoken about the conflict problem, right? So let's move on to issues. So here, if you see, I have written conflicts as there are multiple masters accepting write for same value. As I said, let's say same document, let's say you have a row, right? In your database you have a row, and that same row is being updated at data center 1, right here. And the same row, if a particular column, let's say address, is being updated at data center 2, and for the same row in the same table, the column address is also being updated at data center 1. Now it's a conflict situation, right? Which value is the correct value, right? So that's the conflict problem. So that's a bigger issue in the multi-master replication setup. You will always end up having conflicts. Now there are many tools, for example, your databases, Cassandra, and many other databases or many other systems. They have been using conflict resolution techniques, right? And then, or some of them has the custom conflict resolution techniques, and some of them are using conflict avoidance things. But although the point is, if you are using multi-master replication setup, you will have to use some way to find the conflict and fix them, right? So if you move on, right, in the issues, so we'll see the way few of the systems handling conflicts, right? So the way is, let's say, because you can fix conflicts in two ways, right? It could be eager or it could be lazy. So let's say eager, when you are writing the operations, let's say data center 1 leader node, write x is equal to, and when it goes to replicate the data to data center 2 leader node, x is equal to 10, but it already has x is equal to 20. So again, it's a conflict situation. So in eager way of fixing conflict, you will try to fix during the write operation, right? Second way, you don't fix while writing operation, rather whenever client is reading the data, you will get, okay, there are multiple versions available, what should I do, right? For example, now if you go here, let me go back and let's understand this in the notepad, right? So let's say this is your node 2, let's say leader 2, right? It's a leader. And then here you have your node 1, right? It is also a leader. And then here you have node 3. This guy is also a leader. Okay. Now let's say client A has written x is equal to 10 here. All right. Now, so let's say client A, and then, or let's say client B has written x is equal to 50 here. All right. Now what will happen? Now the problem is, you see, this for the same value x, client leader node 1 has the value 10, and for the same value x, node 2 has value 50, right? So this is a conflict situation. Now when it will try to replicate data, right, because it will try to propagate the data because write operation has happened, right? And same thing will happen from here as well. But let's try to understand the first scenario. When it will try to understand, you see here in this case it already has 50, right? And now you are saying x is equal to 10. Now what to do? So that's again basically it's a conflict situation. Alright, so this is conflict. So now there is one way, either during the write you fix this, right? During write operation you fix this, or now let's say this is your node 1 and then this is your node 2 and then this is your node 3. Alright, so now this guy has written its values this, and node 1 has already 50, right? And then now this has replicated, it will say replicate x is equal to 10. Now x is equal to 10, right? Now from here, now your client A want to read the value x, right? Client A want to read the value x. Now what will happen? Client will get two versions, right? Version 1 x is equal to 10 and it will say x is equal to 50, right? So now in this case if you see, alright, so in this case if you see for the same value x, right, node 1 has data is equal to 50 and also node 1 has x is equal to 10, right? So when client A tried to read the value from node 1, it received the x is equal to 10 and x is equal to 50, right? So one way you can solve the conflict is, what you will do, you have already exposed the data to client, right? You have already exposed this data to client. Now you are asking client to fix your conflicts, right? You are asking client to fix your conflict. You are saying, okay, these are the two versions I have. When client is trying to read the operation, you are saying, okay, these are the two versions I have, can you resolve it, which value do you prefer, right? So this is the conflict resolution technique that people use to fix whenever you find the conflict during the read operation, right? So that's why I have written exposing to client resolution to clients, right? So this is one technique. Second technique I have said, last write wins, right? Last write wins. Now what do you mean by last write wins? And also again understand, although last write wins is a solution resolution technique, but this is not 100% resolution technique, right? There are some techniques that can resolve conflict probably, but we don't know. It's under research. Replication is a very big topic to research and still under research. Many organizations, if you see Amazon and AWS, all these Amazon, AWS, they have implemented Amazon DynamoDB, right? They are also using conflict. Cassandra is also using kind of last write win resolution technique to fix the conflict, right? And so many organizations, they are coming up with the revolutionary techniques to solve the conflicts during the write or read operation. Now let's understand what does it mean by last write wins, right? So if you move on, so now let's say there is one operation that N1 happens, right? So N1 happens, N1 inserts a record X, right? And then in N2, node 2, this let's say it also insert record Y, and then N3 it, let's say, updated X is equal to 10, right? When it created X is equal to 10, right? Then what N2 did is insert X, not insert, let's say update X is equal to 100, right? So what you're doing is, in this particular case, last write wins. If you see, node 1 has done some operation in X, node 3 has done some operation in X, node 2 has done some operation on X, right? So these 3 operations are interrelated, correct? Now, how can we understand that the X operation at the N1 happened before the N3 and before the N2, right? So one way is you use kind of an ID some kind of unique ID, right? And then you will associate that particular ID with all the operations, right? So let's say you are appending a timestamp, right? Let's say you are appending a timestamp T1 here, and then when this happened T2 here, and then this happened T3 here, all right? So now, as part of LWW, last write wins, the way any node will try to resolve the conflict is it will say, okay, because now you see all these operations happened right at particular nodes. Now, as part of multilater, what happens? They propagate the right operands to each other, right? That's how it works. Because if N1 has done X is equal to 20, it will also try to propagate it to node 1, node 2 and node 3. If N2 has done insert is equal to Y, it will try to propagate it to N3 and N1, and N3 has done update is equal to X is equal to 10, it will try to propagate it to N1 and N2, and same N2 will try to propagate this exchange to the N1 and N3. Again, people will end up having multiple conflict situation, right? So let's say these are happening at same time. Now last write wins will say, LWW will say, last write wins will say, based on the timestamp, whatever was the latest timestamp, I'll assume that was the correct value. So what was the correct value? This value, right? Because this happened at the last X is equal to 100. So it will say this is the correct value, right? So this is the conflict resolution technique using LWW. Alright. However, you need to understand the major issue with last write win technique is this: you are trying to rely on the timestamp, right? You are trying to rely on the timestamp. Now think about, it's a distributed system. When I say distributed system means, let's say this system, this system, this system, this system, these are connected to each other, correct? These are all connected to each other, but you can say this may have a different timestamp. Maybe there is some delay for any network glitch, for any infra issue. This may have some different timestamp. This may have some different timestamp. This may have some different timestamp. You cannot assume that all the nodes are across the network distributed system. All nodes have the same timestamp, right? It's not possible. It could be possible, but most of the time it's not possible. You always have to assume that this is a fallacy. It's a fallacy situation. You will always having a different timestamp in distributed system. So this solution is not 100% perfect solution. Again, that's again a problem. All right. So now let's go back and see the third thing is casualty tracking algorithms, right? So this is an interesting topic, and I'll create a totally separate video. So this topic, casualty tracking, right? The problem of casualty and the casualty, that actually is a part of consistency. So in some days I'll be creating a video on consistency models, where we will be discussing strong consistency, weak consistency, and the eventual consistency and the casual consistency. As part of this video, we will be discussing about casualty tracking algorithm. But by end of this lecture, I will be explaining this. Before understanding casualty tracking algorithms, try to understand topologies, and then you will be in situation to understand more better, right, the casualty problem. So this is your multi-master topology. So in multi-master topology, you see, if you see this slide, you see all your data center leader nodes, right, how they are connected to each other. But logically, there is some topology is being followed among the distributed system. The way they have been deployed, the way they have been talking to each other and sharing the data and propagating the right operations, right? So there is one topology is being followed in multi-master replication. So there are several topologies. So let's try to do a deep dive into it. So one is circular topology, right? This one. So what happens in this one is each node each leader node, right? Let's say this is leader node 1, 2 and 3 and 4. When this guy will receive the data and write it locally, it will propagate it to next leader node. Now this understand this node, it will write it locally and propagate it further here, and it will write it locally and write it further here. Simple, circular, everything going in a circular fashion. Star topology, you designate one node as the kind of a coordinator. What happens is so these write operations, right? This guy coordinate with the other nodes and propagate the write operation from here to here to here. And if this happens here to here to here. So this is kind of a star topology. Second thing, all-to-all topology, which is majorly used among the distributed system in case of multi-master application, is all-to-all topology. And also, you need to understand this all knowledge and the data that I'm sharing with you. This is being collected from multiple places, because I have also learned it from multiple places, right? So one is that one source is you can read this book, right? This book, Principles of Data Intensive Application. So this book has a lot of knowledge about these replications and other techniques, right? I would suggest you to prefer this book and read it thoroughly. So in the all-to-all topology, every node can talk to each other, right? If you see, all arrows goes to all nodes. This node can directly propagate a write operation to this node. This can here, this can here. So each other, they are very strongly interconnected. They can basically propagate write operation to each other, right? So that's the all-to-all topology. Now, if you see, right, there is a bigger problem in all topologies, right? In the whole, I would say, multi-master replication in each topology. The problem is, I was talking about some time back, I was talking about that in node 1 there is insert x is equal to 50 happens, then x is equal to 20 happens, x is equal to 10 happens. Then how will we understand that the one operation happens before one operation, right? So we said, okay, we will use a unique identifier, let's say id. We will keep the we'll use the value timestamp for that id, and based on the last events we will say, okay, this is the correct value. But again, that's not the correct solution. I mean, it's not the foolproof solution, right? Because distributed system time clocks can have different times. That's the biggest fallacy of distributed system. So even if you see here, I'll tell you the problem again. You will end up in a situation of which is known as problem of causality, right? So now if you see here, this is the problem of causality. Now if you see, let's say you have 3 leaders distributed across 3 different data centers, and then here your client create a P record at leader 1, all right, and then at the same P record, client B updated its value to some XYZ value, but that write happened at data center 2, leader 2, right? And this happened at leader 1, let's say. So because each node can accept, each leader can accept write operation, so there are 2 write operations. One happened at leader 1, creating a P record, and after some time leader 2 updated the P record to, let's say, XYZ. Because leader 1 replicated the P record to leader 2, this the assumption, right? Now let's say your leader 3 was in a different data center and it got disconnected due to network, or let's say for any reason, or let's say it's running behind, right? There is a replication lag with leader 3. Now the way leader 3 accepted the write or received the write is, it received the update operation of P before the create operation of P, right? So actually you are trying to update a P record which is not even created at leader 3. So again, this is known as the problem of causality, right? So so this is also known as causal consistency, right? So the way you maintain this causality is using causal consistency. So if you, I don't know if you have noticed or not, if you look at the commenting system of Facebook, or let's say any social media, you must have noticed that if you comment something, right, it's not like that. If let's say 10,000 people have commented on a famous post created by a celebrity, so you will always end up having values 10,000 value after before its correct value, the correct numerical order, right? It's not like that. Your comments are casually consistent, right? I'll explain you how. So now let's say you have people are commenting on a post, right? Try to just quickly try to understand consistency, right? Consistency. So casual consistency is people are writing comments, right? So there is a post and many people are writing comments, right? So these are your comments. So let's say somebody has written a comment which is at number 5000. So it's not like that. So you will always end up watching this 5000, the comment which is at line number 5000 before 49999 line, right? Comment, because it doesn't matter, right? Many people are commenting. It doesn't matter that if you see this 5000 comment before the 499 comment, after 49999 comment, right? Because these comments are casual consistent. What matters is, let's say if somebody has written, let's say, good looks, right? This is comment number 1, or let's say comment number 14. Now what matters is all people who has replied to this person. Let's say I have written thank you, thanks. So this is a comment, let's say 27, and then somebody has say welcome, and then this is comment 88, right? So if you see these three right operations, right operation 1, right operation 2, right operation 3, these are all casually related. How? Because see, you cannot have thanks before your good looks, this comment. You cannot have welcome before your thanks, right? So this is casual operation. So if you assume that this is your X operation, if you assume that this is your Y operation, if you assume that this is your Z operation, then your right X have happened before your right Y, and this happened before your right Z. So these operations are your casually related operations, right? So that's what I was trying to explain you in the other slide, that that is the problem of casuality. If you go back and you understand, you will get the same scenario, right? Because P record created first and then it updated first, but leader 3 received updated first and he created then later, right? So that's the problem of casuality, because it should be casually consistent in the way that leader 3 should always get the created operation first and then the updated operation. Now in order to solve the problem of casualty, I'll be creating a separate video of consistency models, and there we will be talking about some different algorithms, for example vector clocks or version vectors, so and so forth, but not in this video, not as part of this video, has already gone like 40 minutes. So but there are certain resolutions to the problem of casuality. As I said, version vectors is one of them, vector clocks. But the point is to fix the casualty problem, or to make the system casually consistent, the point is to use the logical clocks, not the physical clocks, right? Because you see, physical clock timing could be different, right? Because you are dealing with the distributed system, there could be delay or anything, infra issue, network glitch, etc., etc. Because of those, you could have different timings. Not all your systems synced at the same time, right? So the point is to use logical clock. Now what is that logical clock, how to implement that, we will be covering in a separate video. So far, just to summarize, we understood what is multi-master replication. We compared it with the single master replication. We also understood that how your multi-master replication works, and we also went through the benefits of multi-master. We said better performance and the tolerance against the data center and the network outages. And then we also understood the problem that Multimaster application comes with, which is the problem of conflicts. And then we also understood that how can we, what are the counters against the conflicts, exposing it to client, and the last right wins, and the casualty tracking problems. And then we also understand what are the topologies that these multiple leaders across the distributed system can talk to each other. And then we also understand the problem of causality, and the solution of it will be coming in the next video. All right, so probably thank you so much, guys. And one request to you guys, because what I have seen is 80% of our viewers in our YouTube channel, they are not subscribed, they don't subscribe, they only watch the content. So if you really like the content, please do a subscribe and like and share this content with your friends, and I'll keep coming. It will also act as a motivation for me. I'll keep coming with the other amazing content. So thank you so much, guys. We will meet in the next video lecture.